Hello and welcome to Game Revolutions, the series that traces my progress writing a 1980s style assembly language arcade game for the Coco. Today we discuss a crucial part of the shoot-'em-up game genre, the shoot-'em-up part. We will develop some explosion animation, watch it not work until it does, and then count down 6 tricks for making hit detection efficient. Why are ears of corn so good at writing device drivers? Because they're used to running in kernel mode. And that was today's corny joke of the week, brought to you by Bing. Bing, try us. We're not busy. So let's start with the artwork that I used to make the explosion. This is the feeblah before it explodes. And then the first frame of the explosion, kind of similar, but it's starting to get a bit squashed. Its vertical length is decreasing and the eyes are getting a bit kind of messed up there. And then you get squashed a bit more. It's a bit shorter. Eyes are still pretty messed up. Now he's pretty much about to go boom. And here he goes, boom. Run the basic program that draws those frames and then pokes them into the beginning of screen memory so it can save them out as binary files. Copy those binary files to my hard drive. Run some Java code to generate the FCB lines. And paste the FCBs into the assembly code. And now a montage of all my fails. The fundamental problem with hit detection is that there's so much to do, so it's a fairly critical routine. Here we've got a snapshot from the game, and I'm just going to make it a bit brighter so you can see the bullets a bit better. So in this example, we have 5 vertical bullets, and never mind that weird triple bullet, that's just a bug, and I'll be talking about that in a future video. And we've got 6 different targets, 6 feeblahs we're trying to hit. So how do we figure out if any of those bullets are hitting any of those feeblahs? Well, one way or another, we have to rule out every possible pairing of a bullet and a feeblah to see if it's hitting that feeblah or not. The way my code is structured, it first iterates through all of the active vertical bullets. And for each one, it will iterate through all of the active feeblahs. And that gives us every possible pairing for which we ask, is this bullet hitting this feeblah? In this example, that could mean iterating that check 30 times because there's 5 times 6 pairs. Now this is the most naive approach you could take. There are other algorithms and data structures that are optimized for answering the question of whether this object is near to this other object. And rather than taking every possible pair, you could ask for a given bullet, what's near it? But if the number of objects is small enough and the overhead of that algorithm or data structure is high enough, it's often not even worth it to do that. And it's still just going to be faster to take the naive approach and check every possible pair. And that is indeed what I'm doing. But then how can I make it faster? The first set of tricks is categorized as early outs. They allow us to skip several iterations in one go, possibly all iterations in one go. Let's say your target only occupies a particular portion of the screen. In my game, the feeblahs are always inside this rectangle. So for any given bullet, before I start checking, are you hitting this feeblah? Are you hitting that feeblah? Are you hitting this feeblah? I can first ask, are you in the rectangle at all? Because if you're not, there's no need to iterate through the feeblahs for that particular bullet. So in this example, I skip the entire inner loop for this bullet here, this bullet here, and this bullet here. Only for the bullets that are shown to be inside the rectangle do I then need to ask which feeblah, if any, is it in contact with. And in my particular game, this is even easier because the width of the rectangle is basically the width of the whole screen. So I don't even need to check the x coordinates of the bullets to ask if it's in the rectangle. I just need to look at the y coordinate. If the bullet is above this top line, early out. If the bullet is below the lower line, early out. And that's exactly what I do. This code is running in the outer loop, but we haven't encountered the inner loop yet. We load D with the offset of the bullet and compare it with the top half of that rectangle. If D is less than, which means it's above the upper side of that rectangle, we early out. If D is below the lower half, we early out. Only if we make it to this point do we start iterating through the inner loop. This one's kind of obvious. This is the picture we've been using this far. When you've got bullets and you've got targets, you iterate through the bullets in your outer loop, and you iterate through each of the targets in your inner loop, and you check for pairs that intersect. But what about now? If there aren't any targets at all, not only do you not need that inner loop because it's empty, but you don't even need the outer loop because there's no reason to check bullets for nothing. So if you keep track of the number of targets that are on screen at a given point, you can check that one number and then rule out the entire search altogether. This next one's kind of obvious. In fact, in some games, this is all you need to do. Before drawing a bullet in its next position, check the color just behind where the bullet's going to be drawn. If you're very careful with the colors of your sprites in your background, this might be all you need to know if there's a hit. In this case, if the background is green, I will just assume there is no hit and we don't need to check any feeblahs. If the color is anything else, then we've got a hit. I still need to apply the bounding box so that I don't accidentally think that bullets up here are making a hit. We want to rule those out first. Now what this scheme doesn't tell you is which feeblah actually gets hit. For that, you'd need a way to go from a particular coordinate in screen memory to the feeblah that occupies that area. And I'm basically just using the inner loop to do exactly that. But in theory, you could have some kind of data structure which maps every single pixel of every single feeblah to the bookkeeping for that feeblah, so that you know that when there's a hit, you can then remove that feeblah from your state. But I'm getting a bit ahead of myself. The main trick here is to early out of the entire inner loop if you're putting that bullet on top of green. Before I added hit checking, these values comprised all the bookkeeping for a feeblah. The interesting piece is this right here, a 2-byte offset into screen memory for the upper left-hand corner of this feeblah. A value like this is very convenient for drawing and then erasing the feeblah. I simply add or subtract 1 to move it left or right, and I add or subtract 32 to move it up or down. But this is not convenient for doing hit checking. I need to ask if a pixel is inside a rectangle. If all I have are offsets, I might have to do some dreaded division. So in order to keep stuff fast, it's reasonable to store the same information in 2 different ways. So once I added hit checking, I kept the offset there for drawing and erasing, but I also added a couple values to keep track of the row and the column of the upper left corner of the feeblah. This means that keeping my data up to date will take a bit more time, because every time the feeblah moves, I now have 3 values I need to update instead of just 1. But doing my hit checking just became a whole lot quicker. I made the same change to the bullet info structure as well. So now bullet locations are tracked not only by a 2-byte offset value, but also by 2 separate 1-byte values representing the row and the column. Now I can do comparisons directly against the rows and against the columns. I don't need to do any modulus or multiplication or division. All the numbers I need are right there. This next trick isn't specific to hit detection. It's really for any sufficiently complex enough algorithm where you just don't have enough registers, and you need to tuck a few registers away for use later. For example, here we're going to use X and D a bit later, but for now we need to overwrite them with other values. So we push them onto the stack, we do a bunch of stuff, and then later we can pull them back out. This is what the stack is for. It's not only convenient, it's very efficient. You only pay 1 additional cycle for each byte that you push, and the cost is exactly the same when you do the pull later. The downside is you are paying 5 cycles in overhead up front. So this turns out to be really nice when you need to push a lot of bytes, but if you're pushing only 1 or 2, you're paying a lot of overhead for that. Is it worth it? Well, there is another way. In this code here, the A register is already filled with the row number for the bullet, and we're going to need it later. Rather than storing it onto the stack, we store it into the instruction stream itself. This looks rather odd. What this operand is referring to is an address of an instruction down below. HCB load bullet row refers to this label, which comes right before this instruction. By writing a value to HCB load bullet row +1, we end up overriding this. You can watch this happen in the debugger. This line in yellow here shows us what we're right about to execute, which is to store the value of A, which is 7E, into the instruction stream at this address. In the window up here, that's this line highlighted in red. So right now the instruction will load A with the value of 0. But keep your eye up here as I do a step. You'll see that that 0 turns into a 7E, which is what A was holding. So rather than tucking away this value for later somewhere on the stack or in some arbitrary memory location, we store it directly into the instruction stream where we're already using a byte anyway. And the advantage of this is we get to use immediate mode addressing for the load. You can see that because of the pound sign right here. A typical extended mode addressing load of A would cost us 5 cycles. If you were taking advantage of the direct page, you'd get it in 4 cycles. But immediate mode addressing is only 2 cycles. Let's compare the cycle counts for just 1 byte. If we were doing it the stack way, a push plus a pull will cost us a total of 5 plus 1 for the push, plus another 5 plus 1 for the pull, so a total of 12 cycles. If we do it the self-modifying code way, the store using extended mode addressing will cost us 5 cycles, plus another measly 2 to give us 7 full cycles for the store and load. So in this case, self-modifying code is faster. What if we have to store and retrieve 2 bytes instead of just 1? Well, now the stack approach starts to show its power because we're only adding an extra 2 cycles onto the base of 5. So it's 7 for the push plus another 7 for the pull gives us 14 cycles. How about self-modifying code? The store is 6 using extended mode addressing, plus a measly 3 to load it back using immediate mode addressing. So again, it comes out faster, 9 versus 14. What about 3 bytes? Now the stack approach takes 8 plus 8, which is 16 cycles, and the self-modifying code uses 6 plus another 5 to do the stores, that's 11, plus another 3 and 2 cycles to do the immediate mode loads, which gives us a total of 16 cycles. It's break even. So once you get to 3 bytes, self-modifying code does not give you an advantage. And some might say it always gives you the disadvantage of code that is harder to read and harder to maintain. But if you were fiddling around with the direct page and you ensured that these stores happened using direct mode addressing, you would shave another cycle off of them and you would still come out on top. But in general, my rule of thumb is once I have 3 bytes worth of temporary data, the stack is probably best for me to use it as a temporary storage area. So in my code, I use a combination of stack sometimes and self-modifying code sometimes. This is our target, the mighty feeblah. In order to determine if a bullet has hit it, we need to check if a bullet has entered the bounding rectangle of the feeblah. We have pointers to memory that contain the column and the row byte of the feeblah, and that is the upper left-hand corner of this bounding rectangle. It has a width of 2 bytes and a height of 12 bytes. Each byte has 4 pixels going across and only 1 pixel going up and down. The feeblah was intentionally designed so that it would take up just 2 bytes of width and all pixels in those 2 bytes would be used. One of the advantages is it makes hit detection a bit easier. Checking if a bullet is inside that rectangle is really doing 2 checks. Is the column of the bullet in the column range of the rectangle? And is the row of the bullet in the row range of the rectangle? Both checks are similar, so we're just going to focus on the column check. In the code, I have the A register loaded with the column of the bullet, and the column of the left side of the feeblah is pointed to in memory. We have a hit column-wise if the register A is between call and call plus 2. I found it easier to structure the code in the negative, to do a check whether the bullet is not in the column range of the rectangle. If not, I can just branch forward and skip whatever would happen next. So my negative check is really whether A is strictly less than the column, or A is greater than or equal to the column plus 2. And here's where a bit of algebra can be helpful. It's very easy to do math against a register, but doing it against a memory location requires loading the value from the memory location into a register and then doing math on that register. So calculating call plus 2 is a bit more complicated. If instead I move the 2 to the other side, now my 2 checks are both against call, and I don't need to change that memory value at all. I just do the first check, A strictly less than call, and if that doesn't pass, then I can subtract 2 from A and ask whether that's greater than or equal to call. And that's exactly what I do. Using self-modifying code, I load A with the value of the bullet's column number. I compare that with the feeblah's column number. And if A is strictly less than, I branch out of there and I move on. Otherwise, I subtract 2 from A and do my second comparison. And if I'm higher than or the same, then again, it's a negative and I just skip out of there. The check for the row, which precedes it, is pretty much exactly the same. There is actually one more trick that I will go over in a future video, and that's about allocating which work you do in each frame of the game. And that is the list of hit detection tricks that I have been taught or discovered while working on my game. And I have now shared them with you, the next generation of 1980s style assembly language arcade game writers. Programmers assemble your code to machine language using an assembler.